Welcome to our Generative AI Masterclass. Today, we explore how to elevate your prompts by creating dynamic templates with variables in Amazon Bedrock. Let us dive into the fascinating world of complex reasoning and query structures. As we transition from simple experimentation in the Amazon Bedrock playground to building robust, enterprise-grade applications, we quickly realize that static prompts simply do not scale. Imagine hard-coding a new, massive string every time a user asks a slightly different question. That would be an absolute nightmare to manage and update. So, how do we solve this architectural challenge? We introduce the concept of prompt templates. A prompt template is a predefined and structured format that serves to streamline the interaction with these models by making the process of prompt engineering more efficient and standardized. Think of it as creating a highly reusable blueprint for your AI interactions. It allows for the dynamic generation of prompts by incorporating placeholders that can be replaced with specific input values at runtime. This simple abstraction means your application can swap out a product name, a target audience, or a specific task dynamically without ever rewriting the core instructions. This is especially crucial when we deal with complex queries that include few-shot examples or extensive system instructions. By isolating the variables from the core logic, we maintain clean code, reduce errors, and ensure our foundational models perform predictably across thousands of user interactions. Are you ready to see how this works under the hood? Let us explore the mechanics of building these templates. This flowchart beautifully illustrates the dynamic template process. The template engine ingests raw user input and merges it with static instructions. This instantly generates a formatted prompt, which is then securely transmitted to the Amazon Bedrock model for processing. To implement these dynamic templates programmatically, we turn to a wildly popular framework, LangChain. LangChain is a widely used framework designed to empower the development of applications driven by language models. It abstracts away the heavy lifting of string manipulation and provides a standardized class for managing your dynamic variables. How exactly does it accomplish this? It utilizes a specific class called prompt template. By creating a custom prompt template via LangChain, you can pass in different input variables on every run. You explicitly define an array of input variables, which acts as a strict contract for what data your template expects. Then, you define the template string itself, using standard curly braces to denote exactly where those variables should be securely injected. This allows you to generate content that's tailored to your specific use case, whether it's responding to customer feedback or crafting personalized marketing messages. Without this abstraction, developers often resort to messy, error-prone string concatenations scattered throughout their application codebase. The prompt template class centralizes your prompt architecture, making it effortlessly testable and highly maintainable over time. Let us inspect the exact syntax required to initialize one of these powerful template objects in Python. Let us dissect this Python snippet. First, we import the prompt template class directly from the langchain.prompts library. Then we instantiate our multi-var prompt object. Notice the input variables array explicitly lists 3 expected keys: leasing agent, tenant name, and feedback from tenant. In the template string, we use curly braces matching those exact variable names. We even wrap the feedback in XML tags like customer feedback to help the model process the structured input perfectly. Observe the anatomy of the prompt template. It splits into 2 core components: the input variables list, which forms a strict data contract, and the template string itself, which utilizes curly brace injection markers to precisely locate where runtime data must be placed. We have successfully defined our template architecture, but a template without data is like a car without fuel. We must inject our variables at runtime. Once your prompt template object is initialized, LangChain exposes a highly efficient .format method. This method takes keyword arguments corresponding directly to the variables you defined earlier. What happens if you forget to pass a variable or misspell one of the keys? LangChain will instantly throw a validation error. This strict enforcement is exactly what you want in a production system to prevent malformed prompts from ever reaching the Amazon Bedrock API. Imagine sending an empty string to an expensive language model. That is a waste of both time and money. Let us look at a practical scenario. We have our property management template. At runtime, we extract the leasing agent's name, the tenant's name, and their multi-line feedback from our database. We simply pass these values into the format method. The engine securely maps the data, replacing every curly brace placeholder with the live data, resolving the template into a pristine, full-baked prompt string ready for inference. Let us see exactly how this .format method is executed in code to bind our live application data to our AI logic. Watch how seamlessly the data injection occurs. We call the .format method directly on our multivar prompt object. We pass Jane as the leasing agent and Isabella as the tenant name. For the feedback from tenant, we utilize a Python multi-line string to pass a massive block of realistic text directly from the user. The output of this method is assigned to prompt data. This variable now holds the finalized, beautifully structured string that we will transmit over the wire to Amazon Bedrock. This workflow shows the execution phase. Live application data and the prompt template object converge at the .format method. A validated injection occurs, guaranteeing all required variables are present, outputting the finalized prompt string for inference. Let us see exactly how this .format method is executed in code to bind our live application data to our AI logic. Watch how seamlessly the data injection occurs. We call the .format method directly on our multivar prompt object. We pass Jane as the leasing agent and Isabella as the tenant name. For the feedback from tenant, we utilize a Python multi-line string to pass a massive block of realistic text directly from the user. The output of this method is assigned to prompt data. This variable now holds the finalized, beautifully structured string that we will transmit over the wire to Amazon Bedrock. This workflow shows the execution phase. Live application data and the prompt template object converge at the .format method. A validated injection occurs, guaranteeing all required variables are present, outputting the finalized prompt string for inference.
Now we elevate our templates from basic text replacement to advanced cognitive guidance. We previously learned about few-shot inference, where providing relevant examples can drastically improve the quality of generated content, especially in specialized industries like finance or healthcare. But how do we combine few-shot examples with dynamic templates? It is an elegant architectural pattern. Inside your template string, you hard-code the few-shot examples as static text. These examples serve as shots for the model to learn from, showcasing how previous briefings were constructed for different products, like a water bottle and a smartwatch. You rigidly define the pattern of interactions, for instance, showing a human request followed by an assistant response, multiple times. Then, at the very bottom of the template string, you introduce the final dynamic turn of the conversation. This is where you inject your variables for the new unsolved task. By offering these examples before asking the model to generate a briefing for the new product, the prompt helps the model understand the desired output format and the level of detail expected. This guarantees that every single dynamic request sent through your application perfectly inherits the structural lessons demonstrated in your static few-shot examples. Let us dissect this masterful few-shot template. We declare our input variables as usual, but look at the template block. We explicitly hard-code example 1, providing both the mock human request for a water bottle and the ideal assistant response. This static block teaches the model the exact tone and structure we demand. Then we pivot to the live task. Now draft a similar briefing for marketing manager. We inject our variables only into the final task, forcing the model to apply the lessons learned from the static example to our dynamic data. This logic map illustrates the dual force of few-shot templates. The engine supplies static few-shot examples, so the model learns formatting. Simultaneously, dynamic variable injection introduces the new problem. The model merges these to generate highly accurate output. We have engineered a highly sophisticated data-injected few-shot prompt. The final step is securely transmitting it to Amazon Bedrock for inference. While you can extract the raw string and use the standard Boto 3 client, LangChain provides a highly optimized wrapper class called Bedrock LLM to streamline this process. Why use this wrapper? Because it elegantly binds your foundational model selection, your inference parameters, and your configured client into a single callable object. You specify the model ID, pass in the Boto 3 runtime client you previously initialized, and provide a dictionary of model KWGE. This dictionary holds crucial settings like max tokens, temperature, top P, and top K. Amazed! Once your Bedrock LLM object is primed, executing the inference is stunningly simple. You just invoke the object, passing in the fully resolved prompt data string we generated from our template. The wrapper handles the underlying API serialization, communicates with the Bedrock data plane, and returns the raw text generation response back to your Python environment. Let us observe this streamlined invocation process in code. Here, we instantiate the Bedrock LLM wrapper. We target the Mistral large model by explicitly defining the model ID. Excited! Inside model KWGE, we strictly control the model's behavior by limiting max tokens to 4096 and dropping the temperature to 0.5 to ensure our output is focused and factual. To execute the generation, we simply pass our pre-formatted prompt data directly into the LLM object. We then perform a quick string manipulation to strip out any leading whitespace, extracting the pure generated email body. Excited! Trace the final invocation pathway. The formatted prompt string and inference parameters are bundled into the Bedrock LLM wrapper. This triggers the Bedrock API execution, yielding raw generated text, which undergoes application post-processing for display.
As you scale these dynamic templates in production, you must obsess over cost and latency optimization. When you inject variables into a massive template that includes thousands of words of few-shot examples or system instructions, you are paying to process those static instructions every single time. This is highly inefficient. How do we mitigate this compute waste? We utilize Amazon Bedrock's revolutionary prompt caching feature. Prompt caching is an optional Bedrock feature that lets you cache repeated portions of your prompts, typically the static instruction or system message prefix, so the model can skip recomputing that part on subsequent requests, dramatically reducing compute and token costs. By storing internal model state checkpoints for matching prompt prefixes, caching can cut input token charges by up to 90% and lower response latency by as much as 85% for supported FMs. To leverage this architecturally, your best practice is to cache only the truly static portion of your prompt, for example, system instructions or few-shot examples, while passing dynamic user inputs uncached, striking the optimal balance between reuse and freshness. Always structure your LangChain template so the static bulk resides at the top and your dynamic variables are appended strictly at the bottom. This diagram visualizes prompt caching efficiency. The massive static prefix is securely cached once as a Bedrock memory checkpoint. Subsequent dynamic user variables bypass full processing, merging with the checkpoint for incredibly fast inference execution and low latency output. Let us conclude by cementing the architectural best practices for dynamic prompt templates in enterprise environments. First, always use highly descriptive variable names in your templates. Avoid generic names like data1 or text. Instead, use exact semantic identifiers like user search query or customer feedback. This guarantees that other developers understand the exact data contract required by the template. Curious? What happens if your application passes a null value into the .format method? The LLM will receive a broken prompt and likely hallucinate. You must implement strict backend validation logic to sanitize and verify all user inputs before they ever touch your prompt template objects. Finally, treat your prompt templates as code. Store them in a centralized, version-controlled repository, or utilize tools like Bedrock Prompt Management. This allows you to rigorously A/B test modifications to the template phrasing without disrupting the underlying Python application logic. Mastering dynamic templates empowers you to build highly scalable, personalized generative AI experiences. We invite learners to like, subscribe, and visit quicktechie.com for premium and Godfather material as per latest syllabus and certification prep. Q&A banks, ebooks, audiobooks, full training, interview guides. On YouTube, it may not be a latest contents. This represents the enterprise workflow. Raw user input undergoes strict input sanitization and validation. The system then fetches the versioned template from a repository, securely performs variable injection, and executes secure Bedrock inference.